Space weather at NASA. Hello, I'm Jim Spann, NASA's Space Weather Lead in the Heliophysics Division. Space weather is a term that is getting a lot of exposure these days. But what is space weather, and what is NASA's role? Why should we care about space weather? I hope after this talk you will have a good sense of what space weather is and why it's important to study it, and what NASA is doing to better understand it. Let's start with what causes space weather. The Sun, our very own star, is the driver of space weather. The Sun is not a quiet ball of gas that quietly sits 94 million miles away, or 499 light seconds away, but it is an active, rotating gaseous spheroid powered by fusion at its core with an internal dynamo that creates its magnetic field. When observing the Sun at different temperatures or wavelengths, we can see its dynamic and periodic violent nature. It emits energy in many different forms beyond the warm sunlight we experience on a sunny day at the beach. Explosive events release copious amounts of ionizing radiation ranging from X-rays to extreme ultraviolet light. Radiation through very energetic particles traveling at fractions of the speed of light, and large plasma blobs that are ejected into interplanetary space. These explosive space weather events are called solar storms. In addition, our Sun has an approximate 11-year cycle during which its magnetic poles flip and create periods of maximum activity when the magnetic poles are along its spin axis, and then minimum activity during the switch. Even though classified as an average G star, likely to end up as a yellow dwarf, its impact on our solar system is anything but average, and understanding it to the point of predicting its behavior is a gigantic endeavor. And this is just the beginning of describing what space weather is. You see, our planet Earth is immersed in the extended atmosphere of the Sun, and understanding the explosive nature of the Sun to the point of prediction is the starting point to understand space weather. The next step is to know how much energy is released by the Sun and how it travels through interplanetary space. Ionizing radiation with energies from X-rays to extreme ultraviolet emitted from solar explosions travel at the speed of light and arrive at Earth in a little bit more than 8 minutes. These blanket the Earth's sunlit atmosphere and change its composition and density. The radiation from very energetic electrons and protons is usually caused by solar flares and travels at a fraction of the speed of light. If the Earth is in its path, the radiation is detected within an hour depending on the magnitude and energy distribution of the particles. Being able to predict the intensity and occurrence of the radiation from these energetic particles is proving to be very challenging. Large ejections of plasma called coronal mass ejections, or CMEs, often occur in multiples, the more energetic ones overtaking the slower ones as they travel away from the Sun. CMEs create conditions for further energization of the plasma and perturbations of its density and contortions of its magnetic field. The time it takes a CME to travel the 92 million miles can be as short as 12 hours or more than 36 hours, depending on the magnitude of the event. These three types of solar storms and combinations are complex, and understanding their nature and impact once they arrive at Earth is what space weather is all about. Using this artist's conception of the Sun-Earth system, we can see that being able to understand all of these concurrent processes driven by massive solar explosions is incredibly difficult, much less being able to predict them. How fast does a coronal mass ejection travel and in what direction? How dense is it? What is the orientation of its magnetic field? How soon will energetic electrons and protons arrive, and what will be their energies? When will an X-ray flare occur? What are the precursor signatures of any of these three types of solar storms? And how can we know when they will occur with enough warning to mitigate their impacts? These are only some of the important questions to answer if we are to understand space weather. And we've not even discussed what happens when a solar storm arrives at Earth, and how it can impact society and our daily lives. Simulations of a coronal mass ejection that strikes the Earth must take into account the interaction of the magnetized plasma and Earth's magnetic field. One can see from this simulation that the Earth's magnetic field shields it from the brunt of the CME by becoming compressed on the sunward side and elongated on the night side. In so doing, Earth's magnetic system, or magnetosphere, absorbs energy from the CME. It subsequently releases that energy as it seeks to reconfigure itself back to the unperturbed state by reconnecting magnetic field lines and funneling the energy down toward the Earth. When a CME that strikes the Earth has its magnetic field pointed down or southward, it can more easily couple to Earth's upward north-pointing magnetic field. This allows a lot of energy to be transferred to Earth's magnetosphere. The result is often a magnetic storm and a very bright and active aurora that expands toward the equator. Understanding this very complex process that depends on many factors such as CME energy, density, and magnetic field, and knowing how effective it will be to generate a magnetic storm is the stuff of space weather research. The aurora, besides being the greatest light show on Earth, is the most visible manifestation of space weather. So far, we have discussed what causes solar storms and how magnetic storms at Earth occur. But why is that important? Why should we care? How does space weather impact you and me? There are many ways space weather affects us, and it is complicated, which is no surprise considering what we have just discussed. Because our society has become so technological and dependent on space assets, space weather impacts are a growing and significant concern. Recall that we introduced three primary products of solar storms: ionizing radiation, radiation from energetic protons and electrons, and coronal mass ejections. Ionizing radiation from an X-ray flare travels in a straight line from the sun. When it strikes Earth's atmosphere, it ionizes the constituents in the daylit upper atmosphere from about 80 kilometers up to 600 kilometers altitude. This does two things. It modifies the reflection and propagation of radio waves affecting communication and navigation systems, and it heats up the region, causing the drag on spacecraft and space debris to change, thus altering their orbit. This is problematic for many reasons. For example, space traffic management, where locating debris in spacecraft is critical to avoid collisions, becomes very much more complicated. And for communications over polar regions that are now more navigable and useful due to climate change can be compromised. Radiation produced by energetic particles follow the arc of the solar magnetic field as it emanates from the rotating sun, also called the Parker spiral. This radiation can reduce performance of spacecraft solar cells, damage spacecraft electronics to the point of losing control of the spacecraft, and affect the health of humans in space, and to a lesser extent, passengers and crew on transpolar airline flights. Coronal mass ejections not only cause magnetic storms that brighten the aurora, but they pump up the energy of radiation belts, can damage spacecraft, and disturb communications and positioning systems, and if severe enough, can damage power grid systems, cables, and railway systems, causing powered infrastructure failures over large areas of continents. Space weather impacts have no regard for geopolitical boundaries and are of global concern. It is calculated that a magnetic storm at Earth similar to what was observed in 1859, known as the Carrington event, or the 2012 Carrington-class event observed in space that fortunately was not Earth-directed, would cause mass disruption to GPS and communication systems and trigger power outages over widespread regions. It is estimated that the economic impact would have been on the order of 12 trillion US dollars and taken years to recover. Yes, we should care about space weather. But wait, there's more. We have only discussed the large or extreme events that may occur once every 10 or 100 years. The reality is that space weather, just like weather at Earth, occurs every day, and everyday space weather is important. For example, understanding whether a spacecraft anomaly or an unexpected signal that is detected is naturally occurring or induced by human behavior is critical for decision makers. Being able to communicate from the ground to space and space to ground is critical for national security. Industries that rely on navigation and positioning systems such as commercial mining, farming, and drilling, or transportation systems, to name a few, play a large role in our functioning global society. Everyday space weather is critical to decision makers, businesses, and to our own well-being. In addition, we are now beginning to understand that the ionospheric disturbances that impact communication, navigation, and positioning systems are also generated from below by terrestrial weather through upwelling gravity waves, regardless of what the sun is doing. Once again, understanding these coupled and complex systems is very challenging and is the stuff of space weather. But you can bet that NASA is on it and paying attention. Finally, let me share some of the things that NASA is doing to better understand space weather, and along with other federal agencies and space agencies across the globe, what we are doing to transition knowledge, techniques, and technology to enable better space weather forecasts and informed decision makers. The NASA Heliophysics Division flight missions form a fleet of solar, heliospheric, geospace, and planetary spacecraft that operate simultaneously to understand the dynamics of the solar system and space weather. Whether it is a large extreme event or everyday space weather, NASA is on point to explore, discover, and understand. This fleet can be thought of as a single observatory, the Heliophysics System Observatory. Experience has demonstrated that combinations of these missions enable larger scale investigations. This distributed observatory has flexibility and capabilities that evolve with each new mission that is launched. Knowledge, data, and new interpretive models facilitate the path toward new scientific understanding and applied to space weather. Included in this fleet is a space weather payload Hermes on the Lunar Artemis Gateway that, together with complementary ESA and JAXA payloads mounted on a Canadian Space Agency structure, will continue multinational space weather investigations in cislunar space as a pathfinder for deep space human exploration. Furthermore, we have recently announced the funding of 4 new space weather CubeSat missions, Dynaglow, Sunset, WindCube, and Cubix. When launched, they will join the Heliophysics System Observatory in its quest to better understand space weather. NASA funds and manages over 70 multi-agency competed research grants in coordination with NOAA, the National Science Foundation, and DoD that are focused on research to operations to research. And NASA is funding space weather efforts for small businesses through the Small Business Innovative Research Program. NASA is playing its part to understand space weather and to enable space weather decision makers and forecasters to contend with its impacts to secure a safe and thriving technological society. NASA plays a vital role in space weather research by providing unique, significant, and exploratory observations and data streams for theory, modeling, and data analysis research and for operations. NASA's contributions to observing and understanding space weather are critical for the success of the national and international space weather enterprise. NASA has a preeminent space weather capability as described by its vision to advance the science of space weather to empower a technological society safely thriving on Earth and expanding into space, and through its mission to establish a preeminent space weather capability that supports robotic and human space exploration and meets national, international, and societal needs by advancing measurement and analysis techniques and by expanding knowledge and understanding for transitioning into improved operational space weather forecasts and nowscasts. Thank you for your time, and remember that NASA is focused on understanding space weather for your benefit and for all of humanity.